I'm Devin Shaffer. I'm an assistant professor of civil and environmental engineering here at the University of Houston. That's me. And today I want to talk to you about membrane separations research here at the University of Houston, focusing especially on direct lithium extraction. All right. And very broadly, the focus of my research here is promoting resilient communities and ecosystems through membrane separations that create and recover valuable resources. And so today, especially, we're looking at recovering valuable resources like lithium from brine streams. And what I want to focus on are covalent organic frameworks, which are a new type of membrane material for liquid separations. And they enable us to start to explore membrane design for different applications like fit-for-purpose desalination, separators for organic batteries, and of course, direct lithium extraction. And this work that I'll be discussing today is funded by the National Science Foundation. And so broadly, the challenge for membrane separations is this permeability selectivity trade-off that limits their performance. And this is for any type of application. And so this is one of the main goals that we have to address. And in general, you're going to see this expressed as some version of selectivity, say it's salt rejection for desalination, versus some version of throughput, which might be water permeability if we're thinking about desalination. And across all types of membranes, all types of materials, all types of applications, there's really this trade-off that appears in which high selectivity is achieved at the expense of throughput. High throughput is only achieved with a reduction in selectivity. And so our goal, obviously, is to move into the upper right-hand corner here. How can we achieve both high selectivity and high throughput to be able to produce clean water or to recover valuable resources in an economic way? So I'll show a couple of these trade-off plots and look for moving into the right upper right corner is generally the goal. Covalent organic frameworks can help us overcome this trade-off because they are crystalline porous polymers. And so they have some unique properties. They have a very high density of this crystalline structural pore network. So in theory, we can achieve high throughput through pore flow because we have a very high density of pores. At the same time, we can achieve high selectivity because we have a very narrow pore size distribution, so we can maintain a high selectivity. So that's been the underpinning theme of a lot of this membrane research. And especially with these covalent organic frameworks, we have the opportunity to tune the membrane pore size and tune the membrane chemistry by selecting different monomers for the synthesis of these covalent organic frameworks. For the frameworks I'll talk about, probably the most commonly studied, we use the central aldehyde monomer, this blue monomer, and then we can react it with different diamine monomers to achieve different types of pore sizes and pore functionalities. So for example, today I'll show you a pyridine diamine monomer. We'll compare that performance to a benzidine diamine and show how we can adjust the pore size just by changing this diamine monomer. Or, for example, we can start to introduce functionality, working with this diaminobenzene sulfonic acid to introduce a sulfonic acid functional group into the pore while maintaining essentially the same size as another type of COF material. We make these membranes as a composite with a very, very thin layer of this covalent organic framework, tens of nanometers thick. It needs to be supported on a support material, and we do that through an interfacial polymerization process. So first, our diamine is introduced in an aqueous solution. We put our membrane at the bottom of this trough. We then overlay that with an organic solution of the aldehyde. These are immiscible solutions. The monomers stay in their organic or aqueous phases. Only at the interface can these monomers react and form a thin covalent organic framework layer at this confined interface. This happens over a long duration, usually 72 hours. After the film forms, we drain the trough from the bottom, we land our thin film COF onto our support, and we have a composite membrane. Here's a photo of what that looks like, the actual reaction and then some of the resulting materials. Even though we form it in two different parts, the support is separate from the COF layer. They actually are very durable, and we're able to subject them to mechanical stress, and they hold up. So they've been very useful materials. We're up to about maybe 50 square centimeters with this kind of trough technique. And overall, as nanofiltration membranes, they do perform very well compared to other commercial and emerging nanofiltration materials. In this trade-off plot, rejection versus permeance, you can see our work highlighted here against some other emerging materials. And we're doing pretty well. We're moving into that upper right corner, achieving high selectivity while also maintaining high throughput. And this was great work led by Dr. Rahul Shevte. So once we kind of figured out how to make these and how to start applying them, how to control their thickness, how to control their pore size and chemistry, my students have started applying them in a lot of interesting ways. Dana Flores, PhD student, is using these as kind of model materials to understand the transport of solutes through nanofiltration membranes. Nanofiltration is an interesting size range where, looking at a cross-section, a pore, we have pore flow, but the pores are small enough that we have charge effects, we have solvent effects, we have dielectric exclusion, we have Donan exclusion. There's lots of things going on. They're sort of convoluted. They're hard to understand. COFs allow us to start controlling these pore properties so we can really model solute transport. Dana made two different materials with the same pore size, but with different charges by introducing the sulfonic acid functional group. Then by applying the Donan steric pore model with dielectric exclusion, she's able to study the relative contributions of different separation mechanisms with these different types of materials and give us insight into solute transport in nanofiltration. Aaron Picton has applied these COF membranes as separators to improve the performance of organic batteries. This is work that's done in collaboration with Dr. Yan Yao here at UH. Basically, they've developed organic batteries, lithium organic batteries, where they're seeing a degradation in performance because a lithium PTO intermediate is shuttling across the separator and depositing on the anode. We developed this COF membrane separator, applied it as a separator in their organic battery. Aaron made the material, characterized its pore size and other physicochemical characteristics. And we saw that it improved the initial efficiency and the overall capacity retention of these organic batteries. Erin's continuing to work with these materials, focusing her PhD research on direct lithium extraction from environmental brines like produced water or geothermal brine. And this is research that is sponsored actually by UH Energy. Erin is a UH Energy Fellow, so we're very grateful for that support. And in this work, Erin's focusing on the lithium extraction process from brines, which is shown in red in this flow schematic. It's very complicated. It involves a lot of separation steps, especially to separate magnesium from lithium. They have very similar physicochemical properties. If we could implement direct lithium extraction in green, we have the opportunity to really simplify this process and to make it more economical and hopefully to increase purity and production at the same time. And so two different applications Erin's looking at using COFs is first for supported ionic liquid membranes, studying what are the performance limiting trade-offs that define the design conditions for a supported ionic liquid membrane to achieve at the system level, but getting down to even the interactions between the membrane and the ionic liquid. And these covalent organic frameworks with their controlled pore sizes and tunable pore properties can be great hosts for very selective ionic liquids to achieve high purity lithium products in direct lithium extraction. The second application we're looking at is engineering the COF pore chemistry to change the solvation environment inside the pore and help facilitate lithium transport directly from the brine feed source. And this is specifically looking at polyethylene glycol chains, which can help dehydrate the lithium and draw it through the pore. And we're looking at trying to scale that up and apply it at a larger material scale based on some initial work promising work that's been reported in this area. And then our initial results have been promising. Erin's shown enhanced lithium transport for materials that have been functionalized in these different ways. So we're excited about the initial results and looking forward to continuing to pursue this in collaboration with some researchers in France. And then finally, kind of commercializing this technology, Erin's very interested in transitioning some of her lab work into the commercial space. And she, as you saw, one of the limitations is really the way we fabricate these membranes. At a liquid-liquid interface, long durations, it's limited in area. We produce large volumes of solvent waste. So it's not a very scalable process. Erin paired with Parisa Taheri, who's also working on these materials. Parisa is working on scaling up the production of covalent organic framework membranes. So Parisa is using electrospray deposition to create these COF membranes, again, COF composites. And she has tested lots of different conditions, different catalysts, different solvents, different electrospray conditions, and basically has shown that we can control the development of covalent organic framework membranes. We can achieve membranes with the same crystalline properties as some of these other techniques, and we can do so much more rapidly and using a much more scalable technique that's electrospray. And she showed that these are the stars here, comparing the interfacially polymerized membranes to the electrosprayed ones. They essentially perform the same. They essentially have the same physicochemical properties, just a much more scalable production. And then we're also looking at durability testing, which is really key for trying to commercialize these. And we see that the membranes perform well in very low pH conditions. They stand up to mechanical stress, sonication, bending. We do see a little bit of loss in performance at very high pH conditions and high temperatures, so we're continuing to study that. And then finally, Erin and Parisa teamed up to really try to start commercializing this and start understanding where this has a role in the marketplace. So together they formed a company called Lithium, and they started, along with Pranjal Sheth, who's very involved in UH Energy as well, he's a finance student, they started exploring the market. They started doing customer interviews, talking to lithium producers, trying to understand if there could really be an impact for this technology. And through these interviews, through their discovery process, they learned that really there is a desire for some sort of plug-in unit that can replace existing water-intensive, chemical-intensive, time-intensive processes like adsorption and like liquid-liquid extraction. So they're very motivated by this idea. They started building a business plan. Even though the technology readiness is still fairly low, they really see a lot of opportunity here. And they started refining that business plan through participating in these student pitch competitions, like competitions hosted by UH Energy. They participated in the DOE Energy Tech Up competition, winning their regional competition and presenting at the national competition. They went to Singapore. It's been this great experience for them to get lots of feedback, meet lots of interesting people, and really help hone their research questions. Most recently, they participated in the Rice Business Plan competition and won the NOV Energy Innovation Prize for their business pitch. So it's been really a wonderful experience. It has shown a commercial path forward, and I would say it's been very motivating for their research and has really helped them refine their research questions. For example, we're focusing a lot on durability because that was a persistent question from the commercial partners. So I really encourage, you probably have students that are involved in things like this. I think it's been a wonderful experience. I think it's been very motivating for them, and it's been very positive for their research as well. So thank you for your attention.
Thank you, Devin. Appreciate that. There's one quick question. We can take it.
Yeah.
Yeah,
the DLE process, did it focus on large or small scale? The business plan that they came up with was a large scale on a sort of on a service basis where they would provide the material, provide the service, and provide the maintenance to like a geothermal brine producer. And then the lithium product would be shared in some, I forget the exact arrangement for the business, but the lithium would be shared, yeah. Sure.
Max temp and min temp?
Maximum and minimum temperature. We're still exploring those bounds. We do see some degradation in performance at 80 degrees Celsius. So we haven't tested the lower end of that, and we're working to try to improve the temperature range for operation.
Thanks so much, Devin. Appreciate that. And